Okay, so this is Tools of Operations Research, lecture number 4. Last week we covered linear optimization. We did it by hand, sketching out a graph, solving generally an objective and constraints in 2 variables, so x1 and x2, or x and y, and that can be done by hand. Tonight we're going to cover more linear optimization problems, more complex linear optimization problems of more than 2 variables, for which we will use Excel and the Analytic Solver platform plugin to solve that for us. Speaking generally about linear optimization, it can be subdivided into different classes of problems that are all linear optimization problems, and we will do some examples of each of these tonight as much as time allows. So the first would be called allocation models, and allocation models are simply where you generally are trying to maximize the objective function subject to having constraints, okay, that require values that are less than or equal to some capacities. That is, you want to allocate some things, but you only have so much that can be allocated. You only have so much to give, and you want to find the best way to give those things out or to divide things up subject to less than or equal to constraints, which are your capacities of how much you could allocate. Covering models are just about the opposite of that. It's where you're minimizing your objective function subject to greater than or equal constraints, which are your coverages. That is, you have to do at least this much, but you want to minimize the amount of work, let's say, that has to be done. But there's a minimum amount that has to be done in each case. Okay, and then we're going to talk about blending models, which are the little more complex problems where the constraints start involving proportions and start involving, so maybe one variable has to be at least 20% of the whole model or represent a value that's 20%. So each variable kind of depends on other variables. That is, you can't just say, well, x has to be greater than 5, or x plus y must be greater than or equal to 5. You say something like, between x and y, x must be at least 50%, the value of y. And so when you're blending 2 of those variables together, we call that a blending model. And those generally can be rewritten or recomputed as a linear optimization problem with just a special form of the constraint. And then finally, if we have time, we'll get to network models, which involve generally the flow of values or of information through a network. For example, a shipping network where you need to ship so much of some product from multiple source locations to multiple destination locations, and you have to figure out how much product should go from each source to each destination, okay, through a network. So that's what we'll cover tonight. So if you remember from last lecture, generally speaking of linear optimization involves an objective function, so something that represents what we want, and we're either trying to maximize that in terms of, say, for example, profit. You want to maximize how much profit you make, or we might be wanting to minimize that in terms of we want to minimize costs or the amount of work to be done. Okay, and that objective function is a function of some kind of inputs, and we're going to call inputs decision variables. They're the things we can decide, the things we can assign values to. So that's what we're trying to decide what to do with, or how much, and we're trying to either maximize or minimize some single objective function. Okay, but then there are other functions which we call constraints, which generally are in the form of inequalities, but they're also just simple linear functions of those decision variables. Okay, and then the goal, of course, is to minimize or maximize the objective subject to all of the constraints being satisfied. That is, if we're trying to be less than in our inequality, then the values we assign to the decision variables is in fact less than that quantity. Okay. And then we worked last week on solving 2 decision variable linear optimization problems, so a problem with 2 variables, and that can be done by hand. Tonight we will work on some more complex models that involve more than 3 variables. We'll start with one that has 3 variables and move on from there to more and more complex. Before we do that, one thing I do want to point out, sort of a definition that we'll refer back to throughout our talks about optimizations, and that is when you have a constraint, that constraint represents a constraint on the solution space. That is, what values can be assigned to the decision variables. And we talked about how the maximum or minimum objective, the goal, always occurs somewhere along those constraint lines. Okay, the constraints can be represented by lines in a graph because they're linear functions, so they're always a straight line, up or down or diagonal in some way. But the best objective function value always occurs somewhere on those lines or somewhere at the intersection of 2 or more of those lines, where those constraints sort of meet up. When you have a solution that meets up at some of those constraint values on the lines of those constraints, we call those constraints binding. That is, the best solution occurs subject to those constraints, right, being met. That is, if a constraint says that x can be no less than 1, and in fact the best objective occurs at an x of 1, then we say that constraint, x must be greater than or equal to 1, is binding. Because if x could have been less than that, we might have gotten a better objective. Okay, so that objective was binding, or kept our objective function from being even better than it could have been. So you'll always have some constraints which are binding in a linear optimization problem, though you certainly could have more than enough constraints that some are not binding. That is, some of them didn't prevent you from getting a better solution at all. So said another way, the constraints that limit the best solution, so what value the best objective function solution could have, we say those are binding constraints. Okay. All right, so let's look at some examples. First, we'll look at an allocation model. So an allocation model, like I said, is maximizing the objective, for example, a profit, let's say, or maybe maximizing your grade in a class, subject to generally less than constraints. So constraints that say some linear combination of the decision variables must be less than or equal to some given value. Okay, and those are values that we'll call capacities. So we're trying to allocate out data, or allocate out work, or allocate something subject to a capacity. That is, we can't over-allocate more than we have. Okay. So here's an example word problem that we'll work through. Say you have a furniture company, and they make 3 different kinds of furniture: chairs, desks, and tables. And each of those products, chairs, desks, and tables, require some work in 3 different departments. That is, there's the fabrication department that needs to sort of make the material. There's the assembly department, which assembles the material together to make the chair or the desk or whatever. And then there's the shipping department that takes the finished product and moves it to where it can be sold. So it takes it to the store, let's say. And let's further assume that we have some estimated maximum potential sales. That is, we think we can sell so many chairs, so many desks, and so many tables before no one else will be buying them. Okay, so you can only sell so much. And we also know how much profit each product can make. So maybe for each chair we can make $5, or each table we can make $10. Okay, so we have those things. Those are known things, and what we want to do is find out what is the best or most optimal allocation of our resources, this fabrication department, assembly department, and shipping department, for making furniture, such that we can maximize our profit, how much profit we make from each product, subject to the capacities, okay? Capacities of the departments and capacities of how much can be sold, okay? So here's some values we'll use in this allocation model. So generally speaking, in linear optimization problems, you'll see tables like this, which are going to give you the parameters, the values to put into the model that represent the various constraints or the various linear functions. So for example, this is telling us that it takes 4 hours in the fabrication department to make every chair. It takes 6 hours in the fabrication department to make every desk, and so on. the fabrication department can only spend 1,850 hours. That's all the time they have available in terms of the number of people and how many hours they can work. Okay, so we have to find a way to say how many chairs should we make, how many desks should we make, how many tables should we make, subject to the number of those product multiplied by these fabrication hours per unit is less than or equal to 1850. Okay, so we can't have the fabrication department working more than 1850 hours, and so on for the assembly department and shipping department. So each department has a constraint on how many hours it takes to build each unit and how many total hours they can spend. Okay. Then there's the demand or the market that says this is the maximum number of product you can sell, we think. Okay, so we can sell 360 chairs, but no more. We think there's just no more people to be buying chairs after that, or 300 desks or 100 tables. And then finally, the profit per unit says that we can make $15 per chair, $24 per desk, and $18 per table. Okay, so we're going to take this information, create in Excel a spreadsheet that represents this information, okay, and then we're going to use the Analytics Solver platform tool or plugin in Excel to tell us how many chairs, desks, and tables should be made to maximize profit subject to each of these constraints. Okay, so just looking at this information, you might think or suggest that because desks make more profit per unit than anything else, that the best profit is likely to be made by making as many desks as we can. Okay, so we can make 300 desks and sell them $24 profit each. So that may be the best profit, right, that we can achieve. Well, maybe that profit is achievable with the number of hours we have for each department. So maybe there's more hours available, we can make chairs or tables. So maybe tables would be next because they make the most profit, and we should try to make some tables with whatever hours are left in each department, and so forth. Okay, so that's what we're going to try to find out. So our intuition says desks are probably the best thing to make. Let's find out if that's true. But first, let's go to Excel and start making our model. Okay. So I'm just going to start from a blank Excel worksheet and kind of walk you through how you can make one of these models. If you get the data that comes with the textbook, this problem comes out of the textbook, and they have an Excel file already built and made to solve this problem. So you can see how they did it, but I'll show you how you can do it from scratch like you would on an assignment. Okay. So first we're going to sort of declare that we have our decision variables. Okay, so every linear optimization problem has decisions that need to be made. And what we're going to decide on is how many chairs, desks, and tables are to be made. So let's just assume for now we don't know how many to make, so we'll say 0 of each. I always find it useful when making a model to sort of fill in the cells in different colors. For example, I always use something like an orange for the decision variables. So these are the decision variables that I need to find the optimal values for. Okay, number of chairs, desks, and tables to make. So from there, we know how much profit can be made from each chair, desk, and table. So if I remember right, let's go back and look. Chairs can make $15 profit, desks $24, and tables $18. So let's put that in. So $15, $24, $18 each, because those are currencies. Let's format those cells to look like currencies. Okay. And now what we want to compute is the sum total profit that will be made. One way we can do that is just take the number of chairs we're going to be making, multiply that by the profit per chair, add to that the number of desks times the profit per desk, add to that the number of tables times the profit per table. Okay, that would be profit. So that would be total profit. Okay, right there. Again, that should be currency amount. So we'll make it look as such. So that's the equation there, multiplying each decision variable by the per unit profit, and then summing those up. In Excel, there's a handy formula for computing patterns just like this. So instead of this, actually I'll do it to the side so you can see, we can use the Excel formula sum product, and the sum product formula takes a range of cells. So here I'm going to select all the decision variables, comma, and then a range of cells to multiply them by one. And what it's going to do is it's going to match up pairs from those two ranges, multiply them, and then add the results all together. Okay? So that will do this sum product of our decision variables and our profits will do the same thing as one by one, multiply, and multiply, and then add them all together. Okay? So that's our objective, is we want to maximize our profit. So I'm going to fill that cell with something like green to represent the fact that that is the objective that I'm going to want to maximize. And then I'm going to have my constraints. Okay? So I have my decision variables, I have my objective, which here is profit. Just label that as such. We'll call that objective profit. And now we have our constraints. Well, what are our constraints? We have constraints for the fabrication department. We have constraints for the assembly department. We have constraints for the shipping department. Then we're going to have constraints on demand. That is, how many chairs can we even sell? And then a constraint on the demand for how many desks can be sold, and a constraint on the demand for how many tables can be sold. So there's only so much demand that people want these products. So we'll create constraints to represent those as well. So for example, the fabrication department requires, well, let's go back and look. Fabrication department requires 4 hours to make every chair, 6 hours for every desk, 2 hours for every table. So I can represent that in the Excel spreadsheet by the number of hours required for each product, chairs, desks, and tables. And then using that same sum product formula, I can multiply how many chairs, desks, and tables I'm going to be making by how many hours it requires for each one. So multiply each of those pairs and then sum all of them together, and that's how many total hours the fabrication department would have to spend to make whatever decision variable, whatever these numbers would be up here. Okay? And I want that to be less than or equal to a certain value. Let's go back and look. So we have 1,850 hours available in the fabrication department. Okay. So I'm going to want whatever this computed value is here, number of hours the fabrication department will take to make all the chairs, desks, and tables that I say I want up here in the decision variables, how many hours the fabrication department will spend doing that, and I'm going to constrain that that must be less than or equal to 1850. Now I've just typed in less than or equal to here just to help us remember that's what the constraint is. It's a subject to this being less than something, and it must be less than 1850. So let's fill in the rest of this for the assembly and shipping departments. So assembly would be 357 2400. 357 2400. Shipping department requires 3, 2, and 4 and has 1,500 hours available. 3, 2, 4 has 1,500 hours available. Okay. Now because I've used the sum product function here, I'm actually going to use absolute addresses for the decision variables. Okay. So I've added $signs before each row number so that I can simply copy that formula down. So now the shipping department, number of hours it's going to spend, is the same B4 through D4, the decision variables, multiplied by B12 through D12, the number of hours the shipping department needs to make each product. And again, these are all going to be constrained to be less than or equal to these capacities, the number of hours available. Okay. Now, for these constraints representing how many chairs can be sold, if I just took 1 times the number of chairs I make, and that was the sum product that I computed. So 1 times the number of chairs, nothing, or 0 times desks, 0 times tables. Sum those up. That's just the number of chairs, literally. And all I'm saying is that must be less than or equal to some demand, okay, which we said was 360. Okay, and then so on. So 360 of those, 300 desks, and 100 tables. And here I'm just going to fill in ones, saying these demand constraints are simply constraints on just the number of chairs, must be less than 3 or equal to 360. The demand of desks say just the number of desks, 1 times the number of desks, must be less than or equal to 300. And then the number of tables must be less than or equal to 100. Okay? So these are the constraints. So let's just, for example, walk through the intuition we had. The intuition says we should make desks. They make the most profit. So we know we can only make 300 desks total. So let's see if we put 300 desks here. It says we can make $7,200 profit. Okay? And you'll see that we're using almost all of the fabrication department's hours, 1,800 of their 1,850 hours. Not so much of the assembly department or shipping department. So they have plenty of hours left. And of course, we are at the constraint of 300 desks. Can't have more than that. So we still have some hours available in each department to make more things. Let's see what would happen if we made a few chairs. So let's say we made 10 chairs. Okay. So it looks like we still have some capacity left. Let's try to make 13 chairs. Now at this point, if we made 13 chairs, 300 desks, we'd get a profit of $7,395, but it would require using 1,852 hours in the fabrication department, for which we only really have 1,850 hours available. Okay, so at this point we violated this constraint. Okay, so this isn't going to work. This solution isn't viable. It requires more fabrication hours than we have. So maybe we can't make 13 chairs. Maybe we can only make 12 chairs. Okay, and so forth. Now, it might be nice if we could see which of these constraints are actually constraining the solution, right? Which of them are binding, let's say. And we can do that in Excel using the if function to say if the computed value equals the constraint value, okay, then we'll just set this cell out here in column H equal to the quote binding value. Otherwise, we'll use not binding. Okay. So I'll let you see that formula there. And I'm just going to drag that formula and copy it down because each constraint works the same way. If the computed value is equal to the constrained value, then the constraint is considered binding. Otherwise, it's not binding. That is, there's still more room for a better solution along that constraint. Okay, the line represented by that constraint. So you can see in this particular solution, 12 chairs, 300 desks, the only thing or only constraint binding that solution, the only constraint keeping that solution from maybe going further is the number of desks that we can make. That's constrained to be 300. So we couldn't go over 300 here. Okay, that's all that's telling us. Well, let's see. We still have some hours available. Maybe we can use them to make one table. Okay? So by making one table, 300 desks and 12 chairs, we've now reached a point where we're constrained by both the number of desks, that's binding, and the number of fabrication hours. That's now become binding because we've used all 1,850 hours of the fabrication department to make this mix of variables. Okay? Does that make sense so far? I want to make sure before we move on, just the building of the model the terms binding, the terms, some product, function, and all of that makes sense. Okay? So we haven't done linear optimization yet. We built the model. We know what our objective is. We know what our constraints are. But we haven't tried to optimize and find the best decision values yet. Okay? All right, so let's try that. If you have Analytics Solver Platform and go to the Analytics Solver Platform menu, you'll see a ribbon named Optimization Model. Okay? So right here, Optimization Model. Okay? On the Optimization Model ribbon, there are 3 buttons: Decisions, Constraints, and Objectives. Okay? Where we're going to put in information about decision variables, what the model can change to try to find the best objective. Constraints, which are constraints that limit what kind of decision values you can use. And then the objective we're wanting to either maximize or minimize. Okay? So what I'm going to do is I'm going to highlight the 3 cells that represent the decision variables, the number of product we can make, chairs, desks, and tables. I'm going to click the Decisions button, and we're going to select the option called Normal. Okay, so these are just normal decision variables that the model can change the value of. Right? It can add to them, subtract from them, set them to whatever value it wants. These are the decisions that we want made in order to optimize something. So decisions normal, after I've selected those 3 cells, and you'll see there's the Analytics Solver Platform has a little screen to the right over here with the title Solver Options and Model Specifications. On the Model tab of that, you'll see a section called Optimization, and it'll tell you what cells are being used for, say, your variables. So here it's saying you have the normal variables in cells B4 through D4. Okay, just what we selected. So next I'm going to select the objective cell. So we were trying to achieve a profit that is maximal. So if I select that cell, in this case E7, click the objective button, I have 2 basic options, whether I want to minimize that or maximize that. Okay, those are the only 2 options we'll consider in this class. And in this case, we'll always choose the normal option, just like we did in the decision variables. So all we're saying is we want to maximize this computed profit. So I'll click that button, and you'll see again on the right-hand side of the screen that it's now listed under objective that E7, cell E7, is being maximized. That's our objective. That's what we want to do, is maximize what value is in E7 by changing the values of the variables in B4 through D4. Okay? So that takes care of the decisions that need to be made and the objective that we're trying to achieve. But now we need to tell it about these constraints. The way we've set the model up, okay, using some product where we've computed values, and then we have next to them the values they must be less than or equal to, makes it very easy to put in the constraints or specify constraints. So I'm going to highlight all the computed values here in column E. These are the number of hours needed in the fabrication department, assembly department, shipping department. These are the number of just literally chairs, desks, and tables being made. These values are the ones I want to be constrained. That is, whatever value gets computed here must be constrained to be less than or equal to something else. So I'm going to select these cells, click the Constraints button. Like with the decisions and objectives, we're always going to use the normal option. Okay, so normal constraint in this class. And in this case, we want all of these 6 values to be less than or equal to something else. Okay, so I can select just the less than or equal to button here. It's going to bring up a smaller screen, a dialog, and saying you're referencing cells E10 through E15, and you're saying you want each of those cells to be less than or equal to something. So here, the something I want them to be less than or equal to, I can click this little button to the left here with the little red arrow on it, and select the cells that I want each of those to be less than or equal to, and you'll see it's filled in G10 through G15. So all this is saying is all the values in the cells E10 through E15, each one must be less than or equal to the corresponding value in G10 through G15. So E10 must be less than or equal to G10, E11 must be less than or equal to G11, and so forth. Okay, so those are the constraints. Let's say OK. You'll see again on the right-hand side, it's sort of listed out the constraints next to the objective, next to the variables, saying we're constraining all the cells in E10 through E15 to be less than or equal to G10 through G15. So that's all we've done. So we've built the model. We've created the spreadsheet that represents here's what we can decide, the decision variables. Here's the objective we want to maximize. And here are the constraints, that is the computed values that we're going to constrain to be, in this case, less than or equal to. Okay? And we've specified to Analytics Solver platform each of those three things, the objective, the decision variables, and the constraints. So now all we have to do, there's a number of ways you can execute to run and find the optimal value. Maybe the easiest way is this big green triangle button here, the play button. If we click that, you'll see it take a few seconds, output some information, and here you can see, well, I'm going to point out two things. One is this text in green right here says that the solver found a solution. All constraints and optimality conditions are satisfied. That is, it found what it considered the most optimal solution. And in this case, it took 4.6 seconds. You'll see a very similar message down here in green saying solver found a solution. Okay? In the case of these kind of models, okay, linear models, it should always be able to find a solution. When we get to more complex models later in the class, there are cases where it might not find the best or optimal solution. Okay, so let's see what did it find. Well, it actually found that the best profit is $8,438, and that's achieved by making 300 desks, like we thought, all the desks you can make, all the tables you can make, and negative chairs. Okay, well, that doesn't really make sense, unfortunately. You can't make negative chairs, which probably simply means we missed adding a constraint. And if you remember last week, we talked about this. Many times there's sort of an assumed constraint that variables must be greater than or equal to 0. That is, you can't choose to make negative chairs. That just doesn't make sense in the real world. So we missed saying that each of these decision variables are constrained to be greater than or equal to 0. That is, you can make 0 of something, but you can't make less than that. So, learning exercise, we missed a constraint, one that wasn't necessarily specified in the problem, okay, but it was assumed that you would know you can't make negative things. Okay? So, if we want to constrain each of these decision variables to be greater than or equal to 0, there's a simple way to do that, which is to just highlight the variables themselves, click the constraints button. We're going to have a normal constraint. And in this case, we want these things to be greater than or equal to. So greater than or equal to button here. And then you can simply put in the value directly, 0, in that dialog. So this just says each cell in B4 through D4 must be greater than or equal to 0. You can't choose values less than that. Okay. If I go back to that model tab on the right-hand side now, you'll see that constraint represented now, that each cell in B4 through D4 must be greater than or equal to 0. We still have the original constraints of E10 through E15 less than or equal to G10 through G15 cells. Okay, so let's rerun the model now. Click the green triangle button again. And now it's computed what it thinks or what it believes is the optimal maximum profit. Again, we see the green message down in the bottom right. Solver has found a solution. Green is good, so it found the best solution in this case. Best profit is $8,400. We made all the tables we could make, that is 100 tables, and we made almost all the desks we could make. So we could have made 300, but we instead chose to make 275. Well, why could we not have made more desks? That is, the market says we could have made 300 desks, but the best profit was to make 275. Okay? So one reason is, well, the reason really is the fabrication department, right, only had so many hours to work, and because the computed value for how many hours they needed to be worked is actually equal to its boundary, its capacity, that constraint is considered binding, which means we could have made more of something had we had more hours in the fabrication department, right? So we made all the tables we could. That constraint is binding, demand for tables. And then essentially we made as many desks as we could until the fabrication department had no more time to work. Now the assembly and shipping departments, they still had extra time, right? They could have spent more time, but obviously you can't assemble and ship a product if you can't if you can't fabricate the material, right? So the fabrication department is limiting the best solution in that case. It is binding. Okay. It is interesting, however, that we chose to make all the tables we could as opposed to all the desks we could. Okay, right? Because technically desks are more profitable per unit, per product, than tables are, and yet we could have made more desks by making maybe fewer tables, but we chose not to, or the best solution, chose not to. Probably the reason should be somewhat obvious, because fabrication department is our binding constraint. Let's look here at how much work does it take to make each desk and table. And the fabrication department takes 3 times longer, 6 hours, to make each desk than it takes to make a table. Okay? So it takes 3 times more work to make a desk. It does not make you 3 times more profit. Right? So profit here is what? About 33% better for a desk over a table. But the number of hours it takes to fabricate those materials is 300% more, right? So in terms of efficient or best usage of our fabrication department, it's better to let them make all the tables they can, because they're easy or faster to make. And then whatever time they had after that was devoted to making desks, which made better profit, obviously, for more work. Okay. Are there any questions about this solution? So again, I'm going to step back and we'll walk through it. So we started with problem description, described some things, what we needed to do, decide why we were trying to decide these things, what our objective was. Okay, so in this case we were deciding how many chairs, desks, and tables should be made by our company. The objective was to maximize profit, okay, so to make the most profit. And then we had constraints that said each chair, desk, and table requires so many hours in each of 3 departments, and each of those 3 departments have a maximum capacity, maximum number of hours they can work. We also had constraints representing just simply how many chairs, desks, and tables were sellable. That is, if you can make this many, you can sell them, but you can make more than that, but we don't think they're sellable. That is, there's no reason to make more than that. We couldn't sell it. Okay, so 6 different constraints, our objective function, 3 different variables. Okay. So you can imagine if you were to solve this by hand, it's 3 dimensions, right? 3 variables, and there were 6 constraints. You would have to find each set of 3 constraints that converge, figure out what values of the 3 variables would occur at that convergence, and what the profit would be, and then of all those different points, which one got you the best profit. Okay? It would have taken me hours to do, and I still probably would have made a mistake. Okay, so the computer was able to do it in seconds. Okay, now it took us time to build the spreadsheet, but in terms of the solution, the computer could find it, in this case, in seconds or milliseconds. Okay. Okay. If there are no more questions, we'll move on. So that was an allocation model. An allocation model is just a linear model that has a objective that you want to maximize, subject to constraints generally being less than or equal to something. Okay, so capacities that represent you can only do so much but obviously the more you do, the more you can maximize something like profit. Okay. Now remember, we did have sort of a assumed constraint that said you can't make negative things. Okay. You can't unmake product to get negative profit and get hours back for each department. Okay. So we also had to add sort of that assumed constraint that all your decision variables must be greater than or equal to 0. Okay. Something to keep in mind. All right. Well, that took care of a linear optimization model. Let's look at another. So another kind of model, similar to the allocation model, is called the coverage model. Okay. And a coverage model, or a covering model, involves basically the opposite. Okay. So it involves minimizing something, say costs. You want to minimize how much costs or how much work has to go into something, subject to greater than or equal to constraints, which represent coverage. So the minimum amount you have to do, the minimum amount you would have to pay, but you want to minimize total payment, minimize total cost, minimize total work. Okay, so that's the next kind of model we're going to look at. Now, I didn't take the time to build a table for the slides here, so I'm going to work off of an example that comes out of the book for that. Okay, values. So what we're going to do in this model is we're going to be making a trail mix kind of product. So you can go to the store and buy these little bags of like peanuts and cashews and M&Ms and all sorts of things all mixed together, right? Just a mix of some things. So we're going to optimize trying to make such a product subject to some constraints that say how much of each ingredient might be necessary. Okay, so for example, if we're making a product mix problem, and in this case our decision variables are going to be how much of each ingredient we need to add into the mix. And there are going to be 5 ingredients, okay? Seeds or sunflower seeds, raisins, bran flakes, pecans, and walnuts, okay? So these are the ingredients that go into our trail mix that we're going to be making as a product. So, I don't know. For now, let's just say we use 1 of each, okay, to get us started. So these are going to be our decision variables. I'm again going to highlight or fill those cells to represent that. Okay, so those 5 decision variables. Okay, so a linear problem of 5 decision variables. Obviously, we have an objective. Okay. Our objective in this case is the cost we have to pay for those ingredients to put into the product. Okay, so we're going to try to minimize that cost. And each product or each ingredient, each of the 5 ingredients have a different cost per pound, let's say. So seeds may cost $4 per pound. Let's say raisins are 5, 3, 7, 6. So these each represent, say, a cost in terms of dollars that we have to pay per pound of ingredient. Okay, and again, we're going to use the sum product function in Excel to say multiply each of the decision variables, how many pounds we're going to use of that ingredient in the product, multiply that by the cost per pound of each of those products, and then sum that up. So that represents sort of the cost of making 1 pound of this product, of this trail mix. And I'm going to fill that cell in green to represent that as our objective. Okay, so this is cost per pound. And then obviously we're going to have some constraints. Okay, so similar to how we built our last model, we're going to have our decision variables. We're going to compute an objective function, which is a function of those decision variables. It's something multiplied by each decision variable added up. Okay, so it's a linear function of the decision variables. And then we're going to have some constraints, which again are just functions that compute some numbers times the decision variables added up that being less than or equal to, or in this case, greater than or equal to some minimum value. Okay. So what are the constraints in this case? Well, the constraints in this case are we want our product mix to have certain nutritional value. That is, each ingredient has so many vitamins that may naturally occur in that product or that ingredient, and we want our total product, the mix of them, to have a minimum content of vitamins. That is, a minimum amount of vitamins for nutritional value. And same essential type of thing for minerals, proteins, and calories. Okay, so these are 4 different aspects of the product that we want to represent its nutritional value, and we want to be able to say it's at least nutritional enough to have so many vitamins, so many minerals and proteins, and so forth. Okay, so what we need to know here is how many vitamins occur in each pound of seeds or sunflower seeds. So again, I'm going to take all these values out of the example in the book. 5, 7, 4, 9, 2, 1, 4, 10, 2, 1, 500, 50, 160, 300, 500. Okay. So each of these values here represent the number of that nutrition, right? That nutritional metric that's in each pound of the decision variable, each pound of the ingredient. So if I use the sum product function again to multiply, and again I'm going to make that a absolute address in terms of the row, multiply each of the decision variables by each of these nutritional metrics per pound, okay, and sum that up. That's going to tell us how many vitamins, minerals, proteins, and calories are in each pound of our trail mix that's made up of, in this case, 1 pound of every ingredient. Okay, and again, we're going to have each of these things be greater than or equal to some minimum, okay, some minimum amount of nutrition. So we want at least 20 vitamins, 20 grams or whatever the metric is of vitamins, at least 10 minerals, at least 15 proteins, and at least 600 calories. Okay? And again, I'm just going to add an easy test here that says if the computed value equals the constrained value, that is the limit, that's a binding constraint. Otherwise, it's not a binding constraint. Add that down. Okay. Is there a question?
Go back to G12. What was the equation?
Okay. So each of these constraints is made up of the sum product of the decision variables multiplied by, in this case, just numbers, okay, just coefficient numbers. So each decision variable multiplied by a different coefficient added up. So we use the sum product function in Excel, okay, and that's the same in that G column for each of the constraints. So the only difference between those formulas is which row of constraint values we're multiplying by the decision variables. So in this case, what we've done is and this represents a decision that we're going to put 1 pound of every ingredient into the trail mix, okay, and we have more than enough vitamins, minerals, proteins, and calories. But obviously, it costs a lot. It's $25 for that bag of trail mix, okay. So what we want to do is find the minimum amount of ingredients we can put in to minimize the cost, subject to still meeting each of the nutritional constraints. Okay. Now we're going to add or specify the model. So we're going to say these 5 values here, B6 through F6, are our decision variables. So decision button, normal. We're going to say the cost per pound computed in G9, okay, is the objective function that in this case we want to minimize, not maximize. We want to minimize that cost. So minimize normal. And then our four constraints are these four computed nutritional values, vitamins, minerals, proteins, and calories, are going to be constrained, just a normal constraint, to be greater than or equal to the corresponding values in the I column, I12 through I15. So G12 through G15 must each be greater than or equal to the corresponding row in I12 through I15. Okay. So that specified our model, right? So we'll hit the solve or play button, the green triangle button, and compute. Okay. And in this case, we got a red error message saying the objective values do not converge. That is, it could not find a solution. And the reason why it couldn't find a solution, if you look, is because it's trying to make 0 of everything, okay, or negative values in some cases of everything, okay, which is not what we want, right? Obviously, we have some minimum amount that we need to put into each thing in order to get each constraint, okay, to be met. So in this case, let's make sure we have each of those specified, G12 through G15, I15, minimizing, okay. Trying to look, make sure I have all the values correct before I do something different. It seems to be computing values lower than. What may be happening, we did forget to say we're constrained that each value needs to be greater than or equal to 0. So that, again, that assumed constraint, you can't have negative ingredients. Let's try that. There we go. So that was the case. So again, forgetting that assumed constraint that you have to put at least 0 of each ingredient in. You can't put negative ingredients in. Represented here. Now, I do want to show you briefly. So on the model tab on the right hand side here, you see we have two different kinds of constraints. One saying some computed values must be greater than or equal to some other values in a cell. But then we have the constraint I added that say each of the decision variables must be greater than or equal to 0. There's another way you can represent that same non-negative constraint. So I'm going to delete the greater than or equal to 0 constraint. And I believe under the Engine tab on the Solver Options panel, there is an option here that says Assume Non-Negative, which means assume that you can't put negative values in for each decision variable. So you should be able to set that to true, Assume Non-Negative, and that essentially adds that sort of constraint that says all your decision variables must be 0 or greater. Okay, so it assumes that they can't be negative. Okay, so I can resolve and get a valid solution. Green message, valid solution. Okay, so what we found was we're going to use roughly 0.47 pounds of seeds, 0.33 pounds of raisins, and 1.31 pounds of flakes for an optimal minimal cost of $8 per bag. And obviously the constraints that we're binding, that is the things that forced us to take at least that many pounds of each of these, were the minimum mineral content, the minimal protein content, and the minimal calorie content. Okay, so probably just looking at the values here, because seeds have a very high calorie content, as high as walnuts, okay, but they're cheaper than walnuts. that forced us to use at least so many seeds in order to get the minimum calorie content we would need, right? And because flakes have a high protein content, more than any other ingredient, right? In order to get our minimum protein content, we needed to use some flakes, okay? And then likewise, the mineral content of raisins is higher, not the highest. Pecans are slightly higher, but also more expensive. So the mineral content of raisins, right, was useful. So many raisins was useful to get us our minimum mineral content. So these three constraints were each binding. That is, each of these constraints prevented us from using less of any of these ingredients to get a lower cost, right? Because we're trying to minimize cost, but we had to get at least this many ingredients of these different kinds to make each of these constraints work. Okay? The vitamin content doesn't seem to be binding. That is, we could have taken less of anything, okay, less of seeds, raisins, or flakes, and we still would have had enough vitamins. That's not the problem. The problem is we wouldn't have had enough minerals or proteins or calories. Okay? Now, we might want to change this model now that we've seen the optimal solution and realized here's the best cost, lowest cost for making this trail mix. We might want to say, well, it's not optimal that we would have no pecans and no walnuts, right? We want to maybe have at least a minimum amount of each ingredient, okay? So let's add additional constraints to represent that, okay? I'm going to add that using the same way we did the demand, market demand for the chairs, desks, and tables in the last example. That is, I'm just going to multiply 1 by each ingredient, okay? So a 1 multiplied by seeds obviously gets me the pounds of seeds, 0.47. 1 multiplied by raisins, nothing else, gets us the pounds of raisins, right? And I'm going to set, and I want each of these to be greater than or equal to some minimum amount. So let's say we want to have at least 1/10 of a pound of each ingredient. So I need to add these 5 new constraints to the model. So I'm going to highlight the computed values. Constraint, normal, greater than or equal to. And I want each of them to be greater than or equal to 0.1, the cell values in I-16 through I-20. Okay. So obviously right now, we don't have enough pecans and we don't have enough walnuts. That is, 0 is not greater than or equal to 0.1. So this is not a valid solution. Now that we've added these new constraints, we need to re-optimize. So I'm going to click the green triangle again, run the model. Okay. So now you'll see, as you might have expected, we use the minimum amount of pecans and walnuts that we've specified. So those are binding constraints. We couldn't have taken less of those. Okay. So the minimum amount of pecans and walnuts, and then whatever apparent mix of seeds, raisins, and flakes to get us the minerals, proteins, and calories needed to meet those constraints, and still get a cost per bag of, well, it says 8. Let's see. Let's give a few decimal places. So a cost per bag of $8.04. Okay. Now, the way we've specified this model, right? So we figured out the optimal mix of products, of ingredients, to make a minimally costed bag of trail mix, subject to some nutritional constraints, and now subject to some sort of minimum ingredient constraints. But now we can start testing different values of this model, right? We can say, what if we required, let's say, at least half a pound of seeds? So right now we're using less than half a pound of seeds. What if we wanted to change that parameter of the model to be at least a half pound of seeds? Okay, let's rerun the model. So now that we've built the spreadsheet, we can change values of these parameters in the model and just re-optimize. And now we can find, well, if you have to have at least half a pound of seeds, then it's going to cost you $8.07 to make a pound of the trail mix. And now, because that's a newly binding constraint, one constraint, the one on calories, is no longer binding. That is, we're having to include so many seeds, so many pecans and walnuts, and then so many raisins and flakes to meet minerals and protein minimums, that we have more than enough calories, not a lot more, but more than enough calories, that's no longer a binding constraint. That constraint is no longer forcing us to take more of something than we might have otherwise. Other constraints are forcing us, but not that. Okay. So if I change that back, 0.1, re-optimize, we should get back to our solution of an $8.04 bag that has the minimum amount of minerals, proteins, and calories, and the minimum amount of pecans and walnuts to minimize the cost. Okay. Any questions about that? Okay. Well, at this time, let's take a break. We'll come back, do some more linear optimization problems. Okay. So let's take a break.